Hello, my name is Philip Krein. I'm a faculty member at the University of Illinois at Urbana-Champaign and also affiliated with Zhejiang University in China. And I'd like to talk today about a basic issue in power electronics. And I hope that you enjoy this session. I hope that you learn quite a bit from other material on Pels tube. So welcome. Hello, everybody. During this session, I'd like to compare voltage sourced and current sourced inverters and give you a fundamental sense of operation and selection. There are some people these days who would claim that one of these is better than the other, but duality is a crucial concept in power electronics. And the point is not that they're better or worse or different. The point is that they both have their own matched situations or unmatched situations. And in any given situation, we might choose one versus the other. And we'll try to explore some of that as we go on during this session. So let's start with the just the very most basic format for an inverter, where basically we just start by saying that there are two sources, an input source and an output source, and I would like to transfer energy between them. And to do that, I'm going to need a set of switches. So at the basic level here, I would start with just a 2x2 switch matrix, and of course it could be more complicated than that. And remember the basic constraints of power electronics. I have to obey KVL and KCL. So I couldn't have both of these be voltage sources because that would mean that I'm interconnecting unlike voltages, which gives me KVL problems. I can't have them be different current sources because that'll give me KCL problems of interconnecting different current sources. So in general, one of them is going to be a voltage, one of them is going to be a current. And that then leads immediately to the conventional, uh, most basic version of the circuit, where I would have, say, a DC voltage source being converted. And here we have symbol problems, but I hope you'll manage to bear with me, to an AC load, which is going to be basically an AC current source. So my input is DC voltage. My output is AC current. And here we have sort of the generic version of a voltage sourced inverter, right? So an inverter, just to remind everybody, is just a generic term for a DC to AC converter. Now you can see immediately, just because of the way we've drawn this, that distinction is not very meaningful. It's just the way I've drawn it. The energy could flow either direction. I could swap my concept of which is the input and which is the output. It really wouldn't change anything about the basic underlying operation. And of course, I could do the dual of that, in which I have a DC current source delivering energy through a switch matrix to an AC voltage source, right? So now we have same general concept here. I've got DC current and AC voltage. So the prior image was a voltage sourced inverter, and now I have a current sourced inverter. So the duality is here, and things go along from there. And as you, I'm sure, would expect, in practice, we're going to have somewhat more complicated circuits. So the most typical voltage sourced inverter is going to have a set of 6 switches interfacing into a 3-phase load or a set of 3-phase AC sources. And in this case, I'm going to show a common neutral connection just for completeness, right? So I have 6 devices here. Right, so here's my basic hex bridge, uh, voltage source converter, voltage source inverter, seeking to deliver energy to a 3-phase load, which could be a grid resource, as we're sort of implying there. It could be something else. And of course, these need to be currents, right? Because I have DC voltage to the input, and these need to be then AC currents. Now, as I'm sure you understand, in the real world, we're not used to thinking about current sources too much. So the practical circuit is going to start with that kind of a format. And then to achieve the current type characteristics that I need out here on the load side, the output side, I want to enforce current-like performance out there. The easiest way to do that is with a set of series inductors. And now these basically can be AC voltages in a 3-phase set coming out like that, right? So there's a typical circuit with then output inductors. Now, without spending very much time on this, grab another color here because I want to emphasize this, right? Typical situation would have basically this part being something like an AC motor. So just about any type of AC motor will look like a series inductance related to winding inductance and the physical construction. And it will have an internal electromotive force, an EMF, back EMF, which will then create this AC voltage source. So this doesn't necessarily imply that we'll always have these inductors explicitly. They may be A, B, and C phases. They may be internal to the actual device, such as a motor. Now, what that also implies then immediately, and let's grab another slide here. What that implies immediately is that a typical application is an AC motor drive. And because in general motors are inductive, it means that the voltage source inverter basically seems like a natural way to do things. Now, unfortunately, that tends to get into some somewhat misleading kinds of situations, meaning that some people get the misimpression that a motor drive is always voltage sourced. Well, we just saw from the circuit that it makes sense for it to be voltage sourced, but that's not really that fundamental. And we'll see some other examples here pretty quickly, right? Another typical application would be renewable energy or some other grid injection resource, right? So let's put that down as well. Typical application. renewable energy. And in this case, the question is, well, what is my DC side characteristic or source? So examples might be a battery or a photovoltaic panel, or, and this is actually fairly common, some other um, AC source that has been processed through a rectifier. Now, that may sound a little bit redundant, but it's actually quite common. Let's say, for example, they have a micro turbine or a large wind turbine that's not necessarily running at the same frequency as the electric power grid. And one straightforward strategy is to rectify that to a DC bus and then send the DC bus into a voltage source inverter, deliver that to the grid. So here we have some of the examples of what happens typically when I have a voltage source kind of a situation. Now, let's just emphasize that a tiny bit, right? So for example, if I had some kind of an AC source and I run that through some kind of, and I'm just going to show it as a block, some kind of rectifier, then I have a DC output here, and very typically we'd have a significant bus capacitor. So here's my C sub bus, tends to be large. And then my hex bridge from here, and I don't want to be lazy here. Let me go ahead and draw it. Right, with inductive connection or filtering out here to a set of AC voltages. Okay, set of 6 switches, right? And this could be, it could be the power grid, it could be a local uh, AC that we're trying to produce for some application, could be any number of things, could be a motor drive, right? So, this represents my output. Okay, so here I have trade-offs because I need this large bus capacitor. I need these inductors, and I may have to make them explicit filter inductors. And then I have whatever's going on here at my source end. Um, and I want to be a little bit careful with this. I don't want to take a lot of time and complexity for it, but it's certainly likely that that set of 3 voltage sources I was just drawing actually represent some kind of passive circuit, not necessarily a real internal source. And I would control these switches, for example, not exclusively, but for example, probably use pulse width modulation to do the job. And we can see that there are going to be trade-offs between the switching frequency and the filter characteristics I would like here at the output, and whether I want to add some other passive components here to make this a multi-pole filter, whether I want it to resonate a particular frequency, and so on. So I'm not trying to cover design issues related to the inverter in this particular short session. I'm just trying to lay out what would be going on here. Now, let me back up. Okay, I want to go back to the generic bridge circuit once again, but with a voltage source. So here's my voltage source, and here is my, remember we have this awkward symbol here, my AC current source, right? I want to think about this just for a bit. Let's think about the switches. Okay, here's B in, here's I out, which is a function of time. If any of these switches are on, they're going to have to carry this current. So pretty obviously, if they're on, they have to be able to carry I out of T, which of course is an AC current, and therefore that's bipolar. When they're off, well, let's see. If one of them is off and I have to have a current path, another one's going to be on here, and I will see a voltage V in across the switch. So when they're off, they have to be able to block V in. So any of those switches has to be able to turn off a DC and hold off a DC voltage, and it's going to have to be able to carry an AC current. I have a symbol for that. I know most people don't like it. Looks like this. Um, a switch that blocks in one direction and carries in both directions. But that's okay. If I go to the store and I want such a thing, I just tell the kind person there to sell me something like an IGBT or a MOSFET, which has this uh, reverse body diode or an explicit internal diode, and therefore indeed has that function. So here's the IGBT version of it. There's the FET version of it, right? So it's not hard to implement these switches, find them, and so forth. And as a result, of course, when you see a voltage source inverter drawn out, most likely you'll see it drawn in a slightly different format here, perhaps with the FETs drawn in explicitly with their diodes potentially implied rather than drawn. Okay, so here's our, once again, our famous hex bridge. Okay. Um, all right, ready to go. And again, there are certain natural applications, such as typical AC motor drives and so forth, right? And I'm not even going to draw that. Okay, so there's a typical hex bridge, the way people normally draw it with the actual devices in place. Okay, let's turn this around and think now more about the current sourced version of it in the time we have here. So let me grab a different color here. Let me draw the DC current source. Okay, and we'll do it first just the 2x2. And down here, this is going to be an AC voltage source. And I look at this and say, well, gee, okay, that may be not so natural for a motor drive, but it might be a little bit more natural for an actual grid interface. So, because the grid may actually have a fairly firm voltage sitting right here. So again, I don't want to imply that this doesn't have any applications. It most certainly does. And there are plenty of places where we might use it. But you'll notice now I have a little bit different, right? Different situation. So the switches, okay, when they're on, in, out. When they're on, they have to carry in, a DC current. When they're off, they have to block V out, which is an AC voltage. So I have a switch now that carries current in one direction and blocks in both directions, looks like that. I can implement that with a GTO. That's a little bit awkward. What most people do today is they try to implement this with an FET or with an IGBT with an explicit series diode. Okay, so there is one example of a reverse blocking switch. Now, one of the things that's changed that has made people begin to revisit this circuit is that there are some of the it's becoming easier, right? But there are some newer wide bandgap devices with inherent bidirectional blocking capability. Okay, so that has changed the equation a little bit in the sense that some of the applications where we didn't look very closely at the current source inverter before are certainly becoming a lot more viable. But let's take another look. Okay, this becomes important. So what happens at my input? Well, maybe I don't have a DC current source. Maybe I have a DC voltage source, and I'm going to put that in series with an inductor. All right. And I have a little bit of limited uh, confidence that my output is really a completely stiff voltage source. For example, if I'm connected to the grid, I have very long connections. I have multiple meters I have to deal with. And therefore, I'm going to need some kind of interface, for example, to decouple connecting inductances and that sort of thing. So the current source inverter, I'm really going to want to have capacitances probably back to the same neutral point. So here I have something that's really pretty much the dual of what we saw before. So this is a very typical three-phase current source inverter. And no, that's not a TV show. It's a current source inverter. Um, so I have to design the capacitance values to do the filtering job. I have to design this bus inductor value and so forth. Now, you might guess, and it turns out to be true, that the design trade-offs are somewhat different, even though duality kicks in. Um, what should I call it? Alternatives or differences or whatever, right? So with the voltage source inverter, I have a large cap. I have series filter inductors. Okay, with a current source inverter, I'm going to have a large inductor, and I'm going to have parallel filter capacitors. Okay, why would I do one or the other? And this was one of the questions that motivated um, setting up this session. Okay, let's go back and look at this. Let's see. If if I'm connected, for example, to the power grid, the actual inductance here, and there will be some, might be fairly small. The capacitors I need to do the filtering job here might also be relatively small. So I have a big inductor, small capacitors, and so forth. One thing that has changed, um, I mentioned already about the wide bandgap devices, um, but another thing that has changed is that many, let me go back to a different color here. Many modern um, permanent magnet machines have very low series inductance. To the point where in some of these machines, we might even have to add series inductance. So this will be a question, right? Do we add more inductance to use a VSI, or use filter caps and go to a current source inverter? And the answer is that some of the experts now are suggesting that this second thing is becoming a much more interesting alternative. So I want to spend just a few more moments here. Let's consider then what the issues might be, right? So voltage source inverters, because of historical basis and so forth, they tend to be familiar, right? And they're very common in AC motor drives. Current source inverters have been unfamiliar, but they're coming back. They're actually quite suitable for grid interfaces, especially as power levels go up. And also, um, they're increasing in use in low inductance drives. Now, few final comments here I just want to make to put this in context. Um, First of all, I want to mention that there's a really, really nice comparative paper from Professor John's group at Wisconsin from APEC in 2024, where they've gone through quite a bit of detail. And basically, what they're able to show is that emerging wide bandgap devices are making current source inverters quite viable And they're actually even able to show controls that generate much lower total harmonic distortion in the load side currents. That's not that fundamental, but especially if the switching frequencies can be raised, which they can with wide band gap, CSI can lead to lower current distortion. And the other really interesting thing is that in a voltage source inverter, in fault situations, um, you're really interested in trying to limit currents and management of fault currents. Okay, in a current source inverter, the dual applies. So faults lead to limiting of voltages, and we need to manage fault voltages. Some people would argue that managing the fault voltage is easier than managing the fault current. It kind of comes down to choosing which kind of thing you prefer and which you want to deal with. Um, so the bottom line, and I think what I'd like to pretty much end with here, right, is that duality and just basic topology of inverters mean that there are both of these voltage sourced and current sourced circuits. Obviously, they both exist. They're both applied. As I've already mentioned, but it's worth repeating, the VSI is common um, because we're so used to that for conventional AC drives. Unfortunately, almost to the point where people say, well, that's an inverter. But in fact, current source inverters, the dual exists um, and likely to have increasing applications. Okay, there are different trade offs, different filtering, different design parameters, which are really outside of the scope of what we're trying to do in this particular session. But as I want to make sure you understand, both exist. Neither one of them is the perfect solution to any given problem. Neither one of them is a bad solution to any given problem. Yes, you're much more likely to see a voltage source inverter in a conventional AC drive situation. But we're seeing current source inverters much more now in low inductance drive applications um, and in some of the grid connected inverters. They were used less because that series blocking switch combination tends to have higher off on state losses. But with the new band gap devices, that distinction is beginning to go away. So in the future, we're much more likely to see a sort of a democratic mix of VSI and CSI circuits for a variety of applications. All right, well, thanks for your attention. I hope this has been helpful, um, and we'll see you next time.